Welcome to the third part of this Introduction to Haskell course, and in this video we're going to be talking about local definitions and conditionals in Haskell. First, we'll look at the layout rule in Haskell, which states that same level definitions begin at the same line position in the script. So the layout rule is used to determine groupings of definitions based only on indentation. Determine groupings of definitions of the same level. So here we can see that in an example, we have a function sum squares. It takes two arguments. The arguments are x and y, but the function body adds together a and b. So what are a and b? They are defined here below using the where keyword. And then we have the indentation rule where both a and b are local definitions that are on the same level and start at the same line in the script. So in this case, the function is sum of squares. So a is equal to x to the power of 2 or x squared, and b is equal to y squared. And then the function body adds these two a and b together. Is it necessary to use the layout rule? Not really. So without the layout rule, we could also write this function using curly braces to specify the groupings. So in this case, our function still wants to add the squares together. And we have, again, the where keyword, but now we have an open and closed curly braces inside which we define the local definitions of a and b. In this case, we have to use the semicolon to separate different definitions. And in this case, the layout does not matter. So this is written as if the a and b definitions begin at the same position, but with the curly braces and the definitions separated by the semicolon, we could have a like this and b could start all the way here. It doesn't really matter, but of course this looks nicer. So there are two ways to create local definitions using the where keyword, which we already saw in the previous example, and there is also something called the let in expression, where the syntax is the keyword let, then we have our declarations or definitions, and then we have in and the expression. So if we want to write the same function sum squares using the let in syntax, we could say sum squares x and y, the arguments x and y, is equal to, so in this function, let a and b be defined here in this expression a plus b. We can also combine both where and let in statements or syntax together. So in this example, we want to check whether the sum of squares of two numbers is a multiple of 5. And we still take in two arguments, x and y, and then we have a one let in expression and one where. So we say let the sum of a and b being the squares, let sum be defined as the sum of these squares in modulo, and modulo is the operator for getting the remainder of division. So here we have we divide sum by 5 and get the remainder of the division. So if that's 0, we know that it's a multiple of 5. So this is basically what the function returns, right? This is the final result, which says it's either equal to 0 or not, true or false. And where contains the local definitions for a and b, which sum uses in the let expression. So what is the difference between these two statements, where and let in? There is a slight difference in that where definitions are accessible to any code above it. So anything we define in below the where as a local definition, we can use it in any code above the where. However, with let-in definitions, the let definitions that we define are only accessible to the in part of the code block. So we saw that the syntax is let, then some definitions, and then in and a code block. So this definition, for example, sum, is only available in this code block, where in this example it is not used. But anyway, let's go through this example because it's supposed to illustrate how not to do this, because this will result in an error. So we want to write the same function in a slightly different way. Instead of doing the modulo operation in the let-in, we want to do it here in the where, and in the let-in we just want to check whether the result is 0 or not. So we define everything as before. We have let sum equals the sum of square a plus b, and then we want to check the result here that it's equal to 0. And then we have the where clause. A and b, as before, they define the sums, the squares of the numbers x and y. And then we have here the result of the modulo operation, where we apply the modulo operator to the sum and divide it by 5. So this doesn't work because sum here in this expression is not available. Sum is defined in the let-in clause here and is only available right here, which is it is not used. So it's not available here, it's not accessible, and this will throw an error. But just on another note, the res, if it was defined properly here without an erroneous call to sum, res would still be available to use here as it is, because res is in a where clause, so anything above the where clause we can use it to the infix operator. So we saw the way that we apply functions is to write a function name and then list its arguments we want to apply it to. But this maybe is not the most readable form, and there is a better one that can be used with functions that take in 2 arguments, and that is with the infix operator. So we wrote functions such as function and then argument 1, argument 2, but we can actually write the argument 1 first, then the function wrapped in these little backticks, and then argument 2. So infix operator is actually the backticks. So our res from last slide could be written as sum and then mod in backticks 2. And this would apply the function mod to the arguments sum and 2. Okay, what about functions with more than 2 arguments? In this case, we still need to explicitly create expression using parentheses. So multiply is a function that takes in 3 arguments, but we can still use the infix operator. So 1 and 2, we apply multiply to 1 and 2, but as we know, this doesn't complete the function. It's only a partial application, which is fine in some cases, but if we want to then apply it to another argument 3, we still need to wrap the first result together. Now we get to conditionals. And conditionals are really a key construct in any programming language and in Haskell as well. And they allow us to make decisions based on certain values. So they are done through conditional statements. And in Haskell, we have a few ways of defining conditionals. So we'll go through all of them now. Starting with the if, then, else statements. The syntax is if a condition is satisfied, then evaluate expression 1, else evaluate expression 2. So condition must always be a boolean. It must always return either true or false for this to work. And both expressions must be of the same type. As you know, Haskell is very serious about types, so it cannot happen that if a condition is true, we'll use a string here, and if it's false, we'll use a number. That doesn't work, as we can see here. So if true, this is a conditional statement that will always evaluate to true, and it will evaluate the then part of the statement, which is 1. But if we say else and then a string value of untrue, this does not work, right? So these two must be of the same type, because they both fill the same place. So let's take a look at an example now, and imagine that we want to create a function that gives some feedback about the track score. It could be some racing track. So it takes in 2 arguments of the float type and returns some kind of a string. So the arguments that we want to take is the time that a contestant achieved and the average time for this track of all contestants. And then we have a if statement where we say if the time of the contestant is less than the average time, we print, okay, great, your time is. Then we use this show, which is used to represent the value of an expression as a string. So we can show an integer to basically cast it to a string, or show a float value or any other value that supports the show method. We can cast them to strings. So we show the difference in the average time and the contestant time, and this is the amount of time, amount of seconds in this case, below the average time of the track. Else we'll print that the time is above the average time. But you may have noticed in the previous example, we have an edge case that's not really accounted for in the if statement. And that is, what if the time of the contestant is exactly equal to the average time of the track? So basically, if we run the function this way. So what will happen is that it will go to the else statement, since 10 is not less than 10. But it will print 0.0 seconds above average, which is kind of okay, but not really what we want. So we can make a third version for this edge case that prints some specific message in this case. So as before, we have the if statement, and then we have the else, and now we say in the else statement, this is called a nested if statement. So we have the first one here, then in the else we have another if. So first evaluate this. If that doesn't work, then another if. And then we say if it's equal to the average time, then we say it's on par with the average time, and else we know that then it must be above, because we check that it's less than here, we check that it's equal here. So if it goes to this else, we know that it's above average, and then we print our message from before. So now if we use this function, we would get this message here. Basically, our function from the previous slide works, but it's using nested if statements, and those are in general considered not so easy to read, especially if there are multiple levels of nesting. They can get quite complicated. So now we're going to look at multi-way if, which is another way of defining if statements, and it might work a bit better for our example. With multi-way ifs, we can create multiple cases without nesting if statements. And we do this by defining a sequence of Boolean expressions, and we call these expressions guards. The syntax looks like this. We have the if keyword, and then we have a series of these pipe symbols that each represent a condition tied to an expression. What happens is, when the program is running, it evaluates these guards from top to bottom, and the first condition that will equate to true, that expression will be then evaluated, and the rest will be ignored. We also have this otherwise keyword, which is sort of like the else statement in the if then else. And that means if you have gone through all the conditions, whatever it is, we'll use this. It's kind of like a default expression for this if statement. It basically just always evaluates to true. Now let's start rewriting our track score example using multi-way if instead of if then else statements. So before we use multi-way if, we have to enable the extension in GHC. We enable extensions in our source code files by using this syntax, which is similar to comments, except it has these hash symbols at start and end, and it uses the keyword language capitalized and then the extension we want to activate. So we put this at the top of our .hs files, and this lets the compiler know to activate these extensions when compiling this code. So once we have done that, we can write code using multi-way if. And one thing to note about multi-way ifs is that the guard patterns that we use must be exhaustive, which means every case must be covered. And to illustrate this, let's look at this example where we rewrite the track score as our first iteration with if then else statements, which didn't differentiate between the case of time being exactly equal to average time. So we have the if, we have the pipe operator for the first condition, which is if time is less than average time, we print the below average message. And then the other conditional is if time is above average time, we print the above average message. If we try to run this function, we will get an exception where it says non-exhaustive patterns in function track score. And this is because the pattern that is not covered is the exactly equal. So time can be less than average time, it can be greater than average time, but it can also be equal to average time. And this function got exactly 10 and 10 equal. So from this code block of if, it does not know what to do with it, and therefore it errors. We can solve this by using the otherwise statement. And if we do have an otherwise statement in the multi-way if, it means we cannot possibly get a non-exhaustive pattern, because otherwise we'll always evaluate to true, and it's the default operation that the code will do in that case. So here we have the, as before, the less than average and greater than average, and otherwise we know that the only other case can be where it's exactly the same, and now this function can work okay. So with this, we have basically the second iteration of our track score function, which covers all the cases, and we can see this reads a lot better than nested if statements. It's all on the same level. It's much easier to understand what's going on in the code, but we even have some other ways to improve it further. With guarded equations, we also use guards, which are expressions that evaluate either to true or false, to decide the flow of the program. And guarded equations allow us to get rid of the if statement altogether. So if we look at this example, our track score is going to be defined a bit differently. So we take in our two arguments, but notice that there's no equal sign here. This is because we're using guarded equations in this case, and the guards are written the same way. So there's the pipe symbol and then the conditional statement, which evaluates to true or false. And then it's the equation sign and what we want the function to do in this case. Then for the next guard, we just simply go to the new line, define it on the same level, and another conditional statement and another equal sign, and the same for the otherwise. So it's very similar to multi-way ifs, but we can get rid of the if keyword altogether. And the important thing is that the equal sign is now not right after the arguments, but after each of the guards. That's why they call guarded equations, because they use the equal sign there. And in the if statements, we used the if arrow. So the equal sign was here, and then each guard had an if arrow pointing to the expression to be evaluated in case the condition is true. The last way to define conditional statements we're going to look at here is the case of expression. And case of expressions use matching patterns, so patterns instead of guards, to determine the expression to be evaluated. So unlike guards, they do not have to be Boolean expressions. They can be, but they don't have to be. The syntax is as follows. We have the case keyword followed by the expression that we are looking at. We are looking at this expression, and depending on the pattern of this expression, we decide what to do next. So we have case expression of, and then our list of patterns. So we can have pattern 1, pattern 2, each tied to an expression to be evaluated. The same as with multi-way if, these are evaluated from top to bottom, and the first pattern that matches will be the expression associated with the first pattern will be evaluated further. The last line here is a wildcard character, which is an underscore, and this matches any expression, any value, any pattern. So it's basically like otherwise in the multi-way if, and to this pattern we assign the default expression we want to use when none of our patterns matched. Here we have an example of a case of expression that will hopefully make things a bit clearer. So imagine that we want to write a function that returns the color of a card suit. This function will take in a string argument and give back a string result. The argument will be the suit of the card, and the result will be the color we give back. So we write the case expression as case suit of. So this means that we're looking at the value of suit and looking for patterns to decide what to give back. We have hearts, diamonds, spades, and clubs as the 4 standard suits, and we assign the red color to hearts and diamonds and black to spades and clubs. We also have a wildcard at the end to say that if we get any other suit that we're not familiar with, we print out this message. Okay, so if we apply the function to diamonds, we get back red, which is fine. And if we give the function something that's not one of our 4 suits, then we'll print out the default message that we're not familiar with. Okay, so that's fine. And the case of expression here, we are looking at suits and we're looking for patterns. In this case, the patterns that we defined, hearts, diamonds, spades, and clubs, are actually complete values of the suit argument, right? So this is one way of defining a pattern, and it's completely fine. But there are other ways that don't look at an exact value for this argument, but instead look for a more general pattern. And we'll get into that in the next video. That's the end of this presentational part, where we looked at local definitions and conditionals in Haskell. And now let's jump into the practical part, where we will explore these concepts a bit further by writing Haskell code. In this practical session, we will go over the concepts that we covered in the presentational part, and those being the layout rule, the infix operator, and conditionals in Haskell. So we'll start with the layout rule, and in the presentation we had this function called sum squares, which calculates the sum of squares of 2 numbers. So let's just rewrite it here. We had sum of squares, it takes 2 arguments, and actually let's write the type signature first because it's the best practice. So we have sum of squares, and we could make it work with any number. So instead of using just ints, we can set overload the type for this function with num a, and then we'll say we accept two a's, which are of type of the type class num, and we return a as well. So that can work with both floating point numbers and integers. And then we had a plus b, where we defined a as x squared and b as y squared. And this should work fine. So if we load our session 3 module is loaded, and some squares of, let's say, 2 and 3 is 13, so it's 4 plus 9, that's 13. And we can also check that it works with floating point numbers. And what happens if we give it one floating point number and one integer? It still works, although the inferred type, in this case of 3, is going to be converted to the floating point. So it's going to be evaluated as 3.0 actually. Okay, so the layout rule is that a and b are defined here on the same level. If we do this, for example, if we define b at a different level, we already get an error in the IDE because this is no longer valid syntax. Same if we try to move it further down somewhere, nowhere works except on the same level. Now we also had the other way of defining these definitions for a and b using curly braces, right? And we said that in this case, indentation doesn't matter, but we have to separate the statements with the semicolon. Okay, so this works fine. If I save, the IDE automatically formats it to this nicer version, but I can also save it without formatting. And now we can see we can put a here and we can put b here, and the indentation does not matter. We can reload this and it will still work the same way. Okay, so that's the layout rule explained a bit further. Now we also talked about local definitions, and we already used the where keyword here to define the local variables for this function a and b. So what if we wanted to use the let in declaration instead? So we would want to say let a and b be equal to this in an expression which would be a plus b, and then we just remove this a plus b and leave it here. Okay, the formatter formats it this way. I don't particularly like, I like this way better, but in any case it's the same thing written with the let in, and it works the same way. Then we also saw we can combine both where and let in the declarations in the same function, and we had a function that calculates the sum of squares but returns whether that sum is divisible by 5 or not. So let's rewrite that here again, and we call it sum squares m5, as in is a multiple of 5. We can write the type signature again. So well, now this should only work with ints, right? Because a multiple of 5 is only ever going to be possible if we have whole numbers. So we take two ints and we return a boolean in this case, because we want to say whether it's true or false, whether it is divisible by 5 or not. Sum squares m5. So we take in x and y, and then the way we defined it was that we said let, I think we used let sum, yeah, let the sum be equal to a plus b in the expression of mod, so the modulo operator or the modulo function of sum and 5 is equal to 0. So equals checks for equality, right? So if the modulo of the sum by 5 is equal to 0, then we know it is divisible by 5, and then this operator will be 0 equals 0, so it will return true. Otherwise it will return false because it's not divisible. And then we also need the definitions for a and b, which we defined in the where clause. So a is again the same, x squared, and b is y squared. Okay, I'll let the formatter format it this way now. And if we reload the module, we now have access to the sum of squares m5. So if we use, for example, 2 and 3, we get false, because what is the sum of squares of 2 and 3? It's 13. Well, I'm just gonna use 5 and 5, which is 50, which is divisible. So this will return true, as 50 is divisible by 5. Okay, so that's the combined let in and where in one function. Now let's see a wrong way of doing this, or a wrong way of using let in and where combined, because we know let in creates super localized expressions which are only available. So for example, here sum is only available in the in expression. And if we wanted to do this a bit differently, so we say here sum is equal to this, and we want to check that res is 0, and we're gonna define res here as the modulo of sum and 5 without equals to 0, just the result. Then this seems like it could work, right? We calculate the modulo here and we check the result equals 0 here, but this does not work. Now I'm not sure if we're gonna get a nice error message where it actually says why it doesn't work, but in any case we get errors. So it's saying something about maybe you haven't applied a function to enough arguments, right? Because sum is like not even defined here. Probably that's why. So it's maybe applying just to 5 or something. Anyway, sum is not available here because sum is defined in the let definition and is only available in this line. So if you try to use it here, it doesn't work. Okay, so I'm just gonna revert this back to this. Okay, and then we also talked about the infix operator, which is the double ticks. And with that operator, we, instead of using functions as function and then argument, we can write them as argument, function, argument. So like we can read it in a more natural way. So for example, here I can replace this by saying what I really want to do is sum modulo by 5. This kind of makes more sense to read it. So because in mathematics we would write this as sum, let's say the sum is 50, and then modulo operator is the percent sign and then 5, and then it's equal to something, right? So this is what we are normally used to when we use some operator to put it in the middle of the arguments. And with the infix operator, this is exactly how we can write the code in Haskell as well. So the last thing we need to go over here are conditionals. And we said that there are multiple ways of defining conditionals in Haskell. We have the if then else statements, we have the multi-way if, we have guarded equations, and we have case of expressions. So we're going to practice those a bit now. And I'm not going to rewrite the functions that we had in the presentation, but instead we're going to work on some katas. And katas are from this website Code Wars, where you can find these so-called katas, which are short tasks that you need to complete using your programming skills. And it's a good way to learn and practice a new language, or practice the one you know. They are of varying difficulty. They can be very easy, they can be very hard. So for this session, I selected 4 katas that we're going to solve here. And we'll start with the multiplication, this one. You probably want to start with this one, but we'll do that a bit later. So for the multiplication one, this is the way to go. The kata is linked here, and I'm going to put it in the description as well, so you can go visit them on the website. But the kata description says the title is simple multiplication, and this kata is about multiplying a given number by 8 if it is an even number, and by 9 otherwise. So this is the starting point we get from the website when we try to do it in Haskell. And now we have to figure out how to implement this description into our code. So first we need to check whether the integer that was supplied is an even number or not. So how can we do that? Well, we can, for this first kata, we can use the if then else statement in general to solve this. So we can say if, and then we want to say if the number is even. So if n modulo 2, right, if it's divisible by 2, then it means it's even. If this is 0, then we know it is even, and what we want to return is n times what? We will multiply it by 8 if it is an even number. If it's not an even number, then we can say else we want to return n multiplied by 9. Okay, now we have some error here. I'm not sure why. Maybe, yeah, okay, it's just scoping probably. Why is this an error? Oh, okay. It's not really an error. So this probably works, right? If we try to load this, so this is from the Katas directory, and it's the multiplication. It does load. Okay, and if we use simple multiplication on the number 5, we get 5 times 9, which is 45. If we use it on 2, we get 2 times 8, which is 16. So this works fine. The editor is saying, why are you using n mod 2 when you can just use even n? Okay, so we don't need to check the 0. We can use this predefined function in the prelude that checks whether a number is even or not. So of course this reads nicer. And okay, that's the first kata done. It's a very simple one, and as we go through the course we'll introduce more difficult ones. Now let's head over to the sex one, and this kata has a bit of a longer description, but in the end it's still a very simple one. Here it explains the male gametes and the female gametes and the X and Y chromosomes, so it's some biology if you're interested. At the end of the day, what the kata wants is for us to return either congratulations, you're going to have a daughter, or you're going to have a son, and that will depend on the chromosome combination that we get. So this kata, this is the starting point we get from the website if we want to do it in Haskell. And you can see that there is no type signature. So let's create our own. And we know actually that what we're going to get is a string that will either be XX or XY. And what we need to return is another string, which is given here, either this one or this one. Okay, so that's the type signature. And then since we used if then else in the previous one, let's use multi-way if here. So that went like this, even though we have only two cases, so multi-way if doesn't really make too much sense here. We'll still use it just to see how it works. So we can say sex receives an argument, which is a string, and we can call it XS, since strings are lists of chars actually. And we can say if XS is equal to XX, then what we want to return is, so if we have the X chromosome, then if we will have a dollar, right? Because both X chromosomes equal the female sex. And now we could say if XS is XY, we'll return the other thing. Now this could be depending on what the kata wants, like maybe there is a test for what happens if neither XX or XY is supplied, but we're not going to worry about that. We'll just consider the only two possible options, arguments to receive are XX or XY, so we can just use otherwise here. And usually in Haskell everything should be lined up. This is like how code is written. I don't really care about that too much. And as you see, my editor switches it this side. That's fine with me. So the hint that we get here is a redundant multi-way if, and we can replace it with a simple if then else statement, which normally we would agree, but we are just doing an example. The other thing is that multi-way if expression needs multi-way if turned on, you see. So this is not going to work. So from Katas we load the sex one, and multi-way if expressions need multi-way if to be turned on. So as we said, usually we put this on the top of the file, but since we have a kata comment here, I think this should still work if it's here. Okay, so this is the syntax for enabling the extension. Then we say language multi-way if. Right, so it's now enabled, and now the only hint we get is, you know, you can replace it with a simple statement, but we don't want to do that. Okay, now it compiles correctly, and if we say sex XX, we have a daughter, and we say XY, you're going to have a son. Okay, so that one is done as well with multi-way if. Let's go to the third kata now. It's called XOR, and this stands for exclusive or logical operator. So we need to implement this operator in Haskell, and it's a logical operator that is not like AND or OR. It's an exclusive OR. So basically the rules for this operator are listed here. In general, it returns true if exactly one of the expressions is true. So one of the Boolean values is true, then it's true. Otherwise, it's false. So if we have false and false, I mean false XOR false will be equal to false. True XOR false will be true because there's one true. False XOR true will be true because there's one true here. And true XOR true will also be false because both are true. And we need exactly one to be true in order to finally evaluate the true. So we need to implement this in Haskell here. And for this one, we're going to use guarded equations. So this is the starting point that we get from the kata for Haskell. And we can just delete this part. And as we know, including the equation sign, because with guarded equations the sign goes further down in each of the guards. So we put the first guard symbol here, and then what we can do is we can just state explicitly the cases in which it is true, XOR will evaluate to true. So that's if we either have, if either A is true and B is false, or B is true and A is false. So we can say if A is equal to true and B is equal to false, then we now put the equation sign and we will return true. Okay, then the other case is if A is equal to false and B is equal to true, then we also equate to true. Okay, what about the other cases? We don't need to state them explicitly anymore, because we can just say otherwise. We know that these are the only two cases in which we will return true, so anything else we will return false. Okay, we get some hints here. A equal true. Why not use just A? Yeah, this is I'm gonna leave it like this because this is fine, but we could say write A. If A is true, then this is true. If A is false, this is false. So if we check whether it's true or not, it's the same. And for B, we check if it's false, so it asks why not use not B, which is the same thing, right? If we, in this case, imagine that B is false, and that would be false equals false, and that's true. So this part would equate to true. What if we instead use not B? If we use not B, not being the negation operator, so if B is true, not B is false. So imagine that B is false and we say not B, then that would equate to true, which is the same thing that this would do. So it's a simpler way of writing it, but for now let's just keep it explicit. Okay, so this should compile fine, the XOR kata. Okay, and now if we have XOR true false, this is true. If we have false false is false. If we have false true, it's also true. And okay, while we're on the note of writing this in a simpler way, I use guarded equations here because I want to illustrate, but there is actually a much more clever and simpler way of defining this XOR, which is, if you notice, the two arguments, in order to be true, they must not be equal, right? They have to be of different values. So true and false, two different values, not equal. False XOR true, two different values. So these are our true cases. And in other cases, true and true, they're both equal. False and false, they're both equal. So instead of this, instead of all these lines, we could actually write just A does not equal B. Right? So this is the operator for not equal. So we have equal for checking equality, and not equals for checking inequality. And for booleans, this works because there are only two values, right? And if we reload it now, we can see that false and true still we get true, and false we still get false, and so on. So that's it for this XOR kata, and let's go to the fourth one now, which is also the last one we have, and it's not really about conditional statements, but we will solve it anyway. This kata is about basically finding the centroid of a triangle or barycenter. So it's mostly a mathematical problem of geometry. If we have some triangle, what we need to find in this kata is the coordinates of centroid. Okay, so it's not illustrated here, but here it is, right? So this point G is the centroid. Here it's defined as the point of intersection of its medians, the lines joining a vertex to the middle point of the opposite side. So right from this point to the middle point of the opposite side of the triangle, this is the median, and then in the intersection of the three medians is the centroid. So what we need to do is apply this formula that shows how to calculate the coordinates of the centroid, and that's x1 plus x2 plus x3 over 3 for the x coordinate, and y1 plus y2 plus y3 divided by 3 for the y coordinate. So where x1 and xx and yx are coordinates of the 3 points of the triangle. So we pretty much have to just apply this formula, except that in this kata it also asks to round the result to 4 decimals, and this is actually going to be our biggest problem. But let's start with just writing the mathematical formula. So the starting point that we get is this one. We have the function bar triang defined as one that takes in 3 tuples, each tuple of 2 elements of the type double, and gives back the result in also a tuple which specifies the coordinates of the centroid. Each of the 3 arguments is are coordinates for one of the points of the triangle. So what we have here in this way of listing the arguments of this function is something called pattern matching, and we'll get into that a bit later in the course, but this is a simple example, so I'm just gonna quickly go over it. So we have basically a tuple here that says A and B, and another tuple C and D, and E and F. So this is sort of like, we could write this function this way. ABC, right? We receive 3 arguments. We can call them ABC. This is fine also. But this automatically deconstructs the tuples so that we can access the first element, the second element of each tuple with a variable. And this is very convenient. So we will use this. So A is going to be our x1, B is going to be our y1, and so on for each of the points. So what we need to do is construct this final tuple with the coordinates of the centroid. And we know that the formula just states to add the coordinates of x and divide them by 3, and add the coordinates of y, divide them by 3 as well. So we're just going to do that, and we know the x coordinates in this case are A of the first tuple, C of the second tuple, and E of the third tuple. We divide that by 3, and the second element of the tuple is the same thing except for the y coordinates, so B, D, and F, and we divide by 3 as well. Normally this is it. We implemented the formula that we are asked to implement. The only other thing to do is a rounding of the result, which is a bit tricky because of, in general, floating point numbers in computer code are a bit weird, and in Haskell we don't have a rounding function. In other languages we might have a function something like round, and then we have our number with some decimal points, and then we say 4, and the result we get is rounded to 4 decimals, like this. We don't have that in Haskell, so we have to use a little trick that I'll just show you here. So I'll show you this in GHCI first. So there is a trick we can use to round up decimal numbers to a certain amount of digits that we want. And let's imagine some floating point number. This one has 4 digits after the decimal point, and let's say we want to round it to just two digits. So if the idea that we can use is that if we multiply this number by a certain exponent of 10, so we can write this as 1e and then to the power of whatever we want, 2, 3, 4. In any case, the number we put is finally going to be the number of decimal places that we want after the point. So this is 1 times 10 to the power of 2. So this is actually 100. We could just write 100, but I find for this it makes it's kind of better to use 1e2, because if we wanted to round to 4, we can just write 4 and so on. Okay, anyway, if we multiply this by 100, we get this part now as, and this is really the part that we want, right? It's 12, and then if we could just get the dot here in front of the 3, 6, it would be what we wanted. Okay, so if we actually round this number that we have to the integer, then it's what we get rid of this part that we don't want, and now we just want to get the dot back here. So how could we do that? We could again then divide it by 100, right? And this won't work, right? This won't work because of types in Haskell. So basically the division operator works with fractional type class of A. If we check the type of this round is an integral, right? So it's just that the types don't match. So what we need to do, we can still do it. We just need to use this method called from integral, and this will convert the integrand to a num class. So we can check the type of from integral, and you can see that in this definition, integral the A type variable will be of type class integral, and the B type variable will be of class num. So it will take a type of integral and convert it to a num type, and num type is what we want to have when we use this division operator. So in that case, this works, and now we have rounded this number to 2 decimal digits after the point. So we just need to, we can write a function for this, like a helper function using the where keyword, and we can call it round to round 4 dp, or just round 4, and we will accept an argument x, and we basically just need to copy our implementation from here. So from integral, except that instead of this random number we use x, and instead of 1e2 we use 1e4 because we want 4 decimal places. And now we have this helper function round, so we can round this whole thing, the 2 coordinates, we can round them to just 4 decimal places, and that should be it for this kata. So if we load barycenter, and then we have the bar triangle function, and then we need to give it 3 tuples, right? 1, 2, 3, 4, 5, 6, and okay, so maybe it's a coincidence that this is exactly right, but if we use some more random numbers, then we will get, okay, anyway, we get a floating point number here, and it's rounded to 4 decimals which is what this kata wants. So that's it for this session. The last kata done. I encourage you to go to Code Wars and sign up, and I think it's a good way of practicing and learning, and you will have these katas that we went through here listed in the description, so you can go through them on your own. And I encourage you to try and open them and do them on your own. Even if you saw the solutions now, try to work them out on your own without looking at the solutions again. You can always come back to it if you get stuck, and feel free to work on other katas to improve your Haskell skills as well. Thank you for watching, and see you in the next video.